Ngalakin Khadijan Nyunga Boja.
Hello everyone, welcome to the lecture of ELEC 4404 in week 3. Today we are going to introduce the very last part of the chapter 1, or part 3 of it. And from next week onward, we are going to start a new chapter, so chapter 2, which is the random process. Regarding the part 3 of the chapter 1, so we are going to introduce the 3 main parts of the contents. The first one is about 2 simple estimators. The first one is called MAP, so maximum posterior estimator, and the other one is ML, so maximum likelihood estimators. So this will be the first section of this lecture. And the second part of this lecture is the introduction to linear estimator. We call that as the linear minimum mean square error estimator. This one is a little bit advanced than the first 2 simple estimators in the first part. Okay, that's the second part. And the third part, we are going to introduce the orthogonality principle, which will be very useful when we move on to the chapter 2 between week 4 and week 6. Okay, let's start our discussion. So in the teaching today, I want to start our lecture from a very simple example. So this example can be used to help us to warm up, to use the knowledge we learned from the week 1, week 2 lectures to understand the background of the estimators. After we understand this question, okay, we move on to introduce the 2 simple estimators. So maximum posterior and the maximum likelihood one. Okay, let's have the question first. Okay, the example is saying, so we got 6 packs of the Tic Tac in a bag. That means, okay, these 6 packs of the Tic Tac are put into a single bag. And out of these 6 packs of Tic Tac, the first pack is the lime flavor. You can see we call that as green color one, okay, the green one. And 2 packs of the orange flavor, so we call that as orange box, okay. And 3 packs of the mixed one. So in other words, we got 1 green, 2 orange, and 3 mixed as the Tic Tac boxes, okay, in the bag. A player will just put his hands, or maybe put his hand into his bag and randomly pick up 1 box, and then open the box, pick up a Tic Tac bin. And of course, out of these 3 types of the Tic Tac box, there are only 2 possible flavors. The lime one in green box, and also in the mixed box. Or the orange flavor, that's maybe in the orange box, or also in the mixed box. Okay, so this is just the whole story. Now, for this question here, let's just got 2 random variables in the whole system. The first random variable, x, denote the Tic Tac box you opened. And the y random variable denotes the flavor of the bin the player picked. Okay, so 2 random variables. Now the question is asking, what is the PMF of the x? Actually, from the condition of the question, we have known this must be a discrete 2 random variable case. And because they are all discrete random variables in the system, so we use the PMF of the random variables as our focus, okay? So what is PMF of x? What is PMF of y? And then what is the conditional PMF of the y subject to x? And finally, what is the conditional PMF of x subject on y? Okay, just these 4 questions. In the following slides, I gave you a lot of details. You may think, okay, the slides are really too long. Not really. Yes, we use several pages of slides, but I tried my best to go through from scratch. And most of them are really simple. If you have already understood or mastered the contents from the first 2 weeks, the slides are too easy. This example is easy, okay? Okay, let's have a look here. As I mentioned, let's start from scratch. So this is a Tic Tac game. So we can treat this one to be a random experiment. And in this experiment, what is the outcome space? Because in this question, we have two random variables. So the box we picked and the bin we picked. So in this case, the final outcome should be the combination of the two random variable values. So actually, we have only 6 possibilities. These six possibilities has already been given in this slide. For example, of course, you can't see it, okay? We just list all the possible outcomes, okay? So you pick a green box and take one orange flavor bin. I know this is totally impossible. We just gave this possible outcome here. Of course, shortly, the probability of this case could be equal to 0. That means this thing is totally impossible. But we just list all the combinations here, okay? So, okay, green box with orange bin. The next one, okay, I open the orange box and pick up orange bin. Third one, I open the mix box and got orange bin. Same thing will be repeated in the next row for the green beans, but the idea remains it. Okay, so in total we got 6 possible outcomes. And okay, this is just, you see, very easy, just one single page. All right. By the way, here before moving on, actually because there's so many like the lemon flavor or orange flavor or the mix box or different beans, so I'd like to use the values of the random variable to denote these different things. So at the bottom of this slide, you can see regarding the tic-tac boxes, I gave them 3 values. So if I say x1 equal to 1, that means I pick a green box for lim, okay? So if x2 equal to 2, so I pick an orange box. If x3 is 3, that means I got a mixed box. So using these 3 values, we are just indicating which tic-tac box you picked from the bag, okay? And correspondingly, regarding the flavor of the bin, there are only 2 options. So lim 1 or orange 1. So I'm using the y1 to denote the lim 1. And I'm using the y2 equal to 2 to denote the orange 1. So after this step, we got only the values of the random variables, rather than the different colors of the boxes and different flavors of the beans. So now we are converting our knowledge, we are converting our observation to the real world cases to the knowledge of the random variables. Okay, now discrete random variable x has 3 values, 1 or 2 or 3. And the discrete random variable y has 2 possible values, 1 and 2. Of course, for the meanings, you can come back to this slide to check them out. Okay. So the first question, what is the PMF, probability mass function of the x random variable? X is the tic-tac boxes. Okay. So let's try to solve this one. Because x is a discrete case, indicating the box opened by the player. So for this discrete random variable x, is PMF is denoted by this thing. And you can see on the right hand side regarding the summation, the I equal to 1, 2, 3. This 1, 2, 3 are actually the 3 possible values regarding the x random variable. Okay, so this is in here. And keep going inside of the summation. The capital P is the probability, and then x equal to xi. This is indicating, okay, what is the probability I open orange box or the green box or the mixed box? So this is used to indicate this probability, and multiple the delta function. This is very general thing. The delta function is just used to indicate the unit vector at a particular position x equal to xi. Because for the unit impulse function, it has the non-zero value only at the position xi in this case. Okay, because it's delta x minus xi. Okay, this is pretty general thing. We have learned this one in I think week 1. Okay, and based on the condition given question, because you have 1 green box, 2 orange box, and 3 mixed boxes. So based on this knowledge, out of all 6 boxes in the bag, the probability I pick up the green box is 1/6, which is given here. And the probability I pick up the orange box, because there are 2 orange boxes, out of 6. So we got 2 over 6 as the probability I pick up the orange box. Finally, because there are 3 mixed boxes, so the probability I pick up the mixed box is 3 over 6. So this is pretty easy. Now let's just plot this thing out. So in this 2-dimensional graph, the horizontal axis is the possible values of the random variable x, and the vertical axis is the PMF value. And we said x1 equal to 1. That indicates the green pack of the tic-tac. x2 equal to 2. This is about the orange pack. And x3 is the mixed pack, which is equal to 3. Okay, and the height of these 3 impulses. So you can see there's 3 blue color impulses in the graph. The height of these 3 impulses indicates the corresponding probabilities of these 3 cases. Okay, so easy stuff. And at the rightmost position, you can see the mathematical expression to the PMF function for this question. Okay. I think this part should be pretty simple for everyone. Okay. So this slide is summarizing the calculation procedure for the PMF of the random variable x, the tic-tac boxes. Okay. Let's move on to the next one. Here, I'm not calculating the PMF of y in this slide. I'm calculating the conditional PMF of the y subject to x. The reason of that is the calculation of the PMF of y is not so simple, not as easy as the x. Okay, so let's just focus on the conditional PMF of y subject to x. So what does such conditional PMF mean? This PMF is actually indicating, okay, I just write on the side. For example, Fy, y subject to x is actually equal to Fy, y. That we have known the value of the random variable x is the given parameter x. Of course, x could be x1 or x2, x3. So this is just general notation. Okay, the physical sense, the physical meaning of this equation is I want to evaluate the distribution of the y when I observe the result of x. Well, in other words, based on this example, that means if I tell you the condition, right? The condition is if I tell you you are opening a green box, x denotes the tic-tac box, right? So you have already opened a green box. So what is the distribution of the flavor of the bean? That could be equal to a lot of them. For example, I want to know the probability that we got the lime flavor of the bean when I open a green box. This is condition. I tell you you are opening a green one. Or what is the probability that you got the orange flavor bean when you open the green box? Of course, the calculation should be simple. This is 100% equal to 1. This is 0%, which is equal to 0. Of course, easy question. So this is just what we want to evaluate. Okay. Of course, for x, we also have different values. For example, open the mixed pack or open the orange pack. Okay, so different conditions. Okay, this whole thing. So what I have explained has already been given here. So this is the conditional probability that we want to evaluate it. Okay, so x, the tic-tac pack you picked is condition, and the flavor of the bean is our interest. Okay. Now, because both x and y are discrete, we need to evaluate this PMF, conditional PMF, as a group of conditional probabilities. X observation come from the possible values of the random variable x. As a result, all possible values of x must be examined one by one, but only 3. Okay. And for each x value we picked, so all possible values of y must be examined as well. At bottom, on the left-hand side, you can see a small table. In the first table, the condition is x1 equal to 1. The random variable value is 1. That means we are picking a green box of Tic Tac. Based on this one, we want to evaluate what is the probability of the Y1, the lime flavor, and what is the probability of the Y2, which is orange flavor bean. So this is evaluating that thing here. Similarly, another possible value of the X is the X2 is 2, which is the orange box. In such case, we evaluate the probabilities of the flavor of the bean respectively and got this result. Finally, if you pick X random variable equal to X3, which equal to 3, that means we pick up one mixed box of the Tic Tac, and then we are evaluating the probabilities of the flavor of the beans. Okay, so I think this part is pretty easy, but after you finish all this calculation, we need to summarize all these things together. And this conditional PMF mathematical formula or expression is showing us this summarized result. When the x1 is 1, y is 1, so this means the green box, and pick up the lime flavor. Of course, the probability is 100%. So in other words, you can repeat this procedure for all the entries in this formula. It's not anything new. It's just the implementation of what we have learned from the lecture 2 to a real case. Okay, so by the end, we reach this answer. This is the conditional PMF when the X is known. And I think this part should be very, very easy for everyone. Okay. Next one, what is the PMF of the Y? Y is the flavor of the bean, right? So for this step, we can't just really analyze the example only. We have to use the mathematical knowledge to help us. So regarding the PMF of the Y, so we want to actually evaluate what is the probability we pick orange or lime flavor bean, and this is a discrete case. So this mathematical equation is very similar as the one we analyzed in the PMF of the X. But how we derive this thing? Okay, here. When Y, random variable Y is equal to Y1, which is equal to 1. So this means we are picking a lime flavor bean from the bag. And we want to evaluate this probability by using such formula. In this summation here, we use the Y1 as our interest, and Xi will be used a condition. Actually, this calculation given here is just using the conditional probability multiple the probability of condition. In other words, this thing is actually evaluating what is the joint probability at Y1 and Xi. For this question, it means what is the probability you pick up one pack and also pick up the lime flavor bean from it? Okay, the joint probability. And then the summation sign is going through all the possible values of the Xi. So that means we examine all three possible Tic Tac boxes and then check the sum up all the probabilities together. Okay, the final result is 5/12. This is the total probability we pick up lime flavor bean from the bag. Repeating the same procedure for Y2 equal to 2 case, this means the orange flavor bean result is 7/12. That's the two cases. Of course, if you add up these two probability together, 5/12 plus 7/12 is 100%. That means you have only two options. So one is lime flavor, one is orange flavor of the beans from the bag, nothing else. This is totally true. Okay. Okay, this is about how to evaluate the PMF of the Y, and then we can just draw this thing out. So Y1 value, Y2 value, they have different probabilities. I think this part should be pretty simple. Okay. Okay, this is the PMF of the y, and let's move on. This is the very last question. So how to evaluate the conditional probability PMF mass function f(x) subject to y? Okay, we need to understand what that means. So the letter y is next to the vertical bar in the brackets. That means the y is condition. Based on this condition, based on this observation, we want to estimate the distribution of x. Regarding again this question, that means, okay, you put your hand in, open the box, pick up a bean out, and then observe the flavor of the bean. That is the y value, your observation. Based on, okay, I can observe the bean is, for example, lean flavor. Then I want you to estimate what is the distribution of the x random variable. Okay, so this is the story regarding this question. And my explanation has been given below in this formula and some statements. You can read them through, so it should be pretty simple. And so we want you to note, first of all, the y observation comes from the possible values of random variable y. So there are only two possible flavors, so lean or orange, 1 or 2 for the random variable y. Okay. And all possible values of y must be examined. Secondly, for each y observation value, all possible values of x must be examined. Okay, so now in the next half of the slide, on the left hand side, you can see this table first. So that means we have already known the condition. So when the y equal to y1, which is equal to 1, okay, lean flavor, right? So you are picking up a lean flavor bean from the bag, and what are the probabilities that you open each of the three possible tic-tac boxes? And in this case, because in each of these cases, we want to evaluate such conditional probability. So we want to use Bayes' theorem and use the joint probability to divide by the probability of the condition. So here you can see we are using the joint probability divided by the probability of the y. Okay, and then on the top of the fraction, that the joint probability will be converted to similar format. Okay, another conditional probability multiple the probability of condition, but in this case we are using x as condition because we have already known the PMF of the x. We have already known the PMF of the py subject to x from the previous 2 or 3 questions. Okay, after all these mathematical formulas, we can put the values into the formula to finish the calculation. Now, out of these 3 cases, if you are picking up lean flavor bean, in other words, if the y1 equal to 1, such conditional probabilities are equal to these values. A very simple thing, but anyway, we just repeat it again. Okay, so let's pick up the first case. What does it mean? This 2/5 result from this calculation is indicating if you are picking up a lean flavor bean from the bag, the probability that you are opening a green box is 2/5. Okay, this thing here. For other entries, the idea is similar. Of course, we just change different tic-tac boxes. Okay. And the other case we need to analyze is the next table. We mentioned we need to examine all the possible values of y, right? The first table examined the lean flavor. So the second table is examining the orange flavor. Got that? I don't think I need to repeat this procedure again because the second table have the same idea as the first table. So just repeating the procedures, please. And by the end, we summarize the result we derived from the 2 tables into a mathematical expression. So nothing new, it's just all the possible combinations of the x and the y and the corresponding values of the probabilities. Okay, so up to now, we have already done all the works regarding this example. So let me check it. I think we have already answered all the questions? Yeah, I think all questions are done regarding this example. So let's quickly review what we have got. In the middle of this slide, you can see I'm assuming this tic-tac game is a system. And the input X are just the packs of the tic-tac. And output Y is the bins we picked. Okay, this is the whole system. Of course, both X and Y are the random variables in our system. So regarding the X and the Y, so far, what we have already solved is this is actually the marginal PMF of the X, marginal PMF of the Y. Because regarding the two random variables in the system, I focus on the distribution of one random variable in these two cases. So they are actually the marginal PMF of X and Y. At bottom, we got the conditional PMF. One is X subjected on Y, the other one is Y subject to X. So these two cases. So these are all conditions we have, okay? And these four important distributions must satisfy this condition. And this condition was introduced in our, I think, week 2 lecture. You may review this part. And deriving this equation is pretty simple. So I don't want to go through it in this lecture. You may try this out by yourself. If you have questions, please let me know. Okay. Easy thing, but important. Okay. Now let's just extend this example. Let's assume you are the player of this tic-tac game, and you will be rewarded if guessing the correct tic-tac box, which was opened by you, according to the tic-tac bin flavor you picked. So in other words, in this case, I will just ask you to pick up a bin from the bag without looking which box you are opening, okay? And once you pick a bin, so take your hand out of the bag and observe the flavor of it. Then you have got your observation ready. So you know which flavor you picked. I want you to estimate which box you opened in the bag. Of course, if you guess the box you opened correctly, I will give you a reward. And for you, if you want to get the reward, what you want to do? At bottom of this slide, you can see this question here, this condition and whole system. Okay, the tic-tac game remains same. So input is X and output is Y. So regarding input, okay, you know there's just one green box, two orange boxes, and three mixed boxes. Okay, the 6 boxes are in the back, and you know the distributions, all this stuff. And then, for example, you pick one green bin out. Now you want to estimate which box you opened regarding the X value actually. Now let's draw this thing out. So in the graph at the bottom, I'm drawing a 2-dimensional graph. The horizontal axis is the Y value. That means your observation, the flavor of the bin. The vertical axis is the random variable X. So in other words, the boxes of the tic-tac. We have mentioned for the Y value, lime or orange flavors. So Y1, Y2, 1 or 2. And regarding X, we have 3 possible values. So X1 equal to 1, this means you got the green box. X2 is 2, which means you got the orange box. X3 is the 3, which means you got a mixed box. Okay, this is just the conditions we derived from this question. And what we are kind of doing regarding this analysis is actually such distribution. So you can observe why we want you to make your final decision based on the PMF of the X. Okay, for example, here we pick up a green bin, so the lime flavor, so Y1 equal to 1. Based on the Y1 equal to 1, see here, the first 3 entries given in this formula is indicating the cases where we pick up the lime flavor, Y1 equal to 1, right? And then you have 3 possible X values corresponding to this observation. x equal to 1 or 2 or 3. So now, when the x is 1, such conditional probability is 2 over 5. So actually, I can't draw a small impulse in this case, right? So I'm using a dot to indicate the 2 over 5. This dot is at position x1, y1. So y1, x1, this position, okay? The value of this dot is 2 over 5. Next one, if the if the y is 1, so Liam flavor, right? And the x equal to 2, which is the orange box, the probability is 0. Okay, you can see here at position y1 and x2, there's no dot. This means 0 probability. Okay, so by repeating these procedures for all 6 combinations of the x and the y, we are going to just highlight all the dots in this 2-dimensional space. The dark color, like this one, which one? This one. This means, okay, the probability is higher, of course. If you got a very light color, this means the probability is lower. So something like that. If there's no dot, so the probability is 0. Okay, this is just an idea. So how to graphically show this into us. Okay, this is just what we have got. But in this particular example, I said, I want you to estimate which one is the most likely box you picked when you observe that you got a Liam flavor bin from the bag. Liam flavor bin means the y, capital Y random variable, equal to y1. So that means we just need to focus on this case. We don't need to worry about the orange flavor bin, right? Now, in this y1 value, there are 2 dots only. And which one is the most likely pack you picked? Of course, you want to select the maximum probability one. So that means out of these 3 entries, you need to pick up the maximum, the one with the maximum probability, which is x equal to 3 case. In other words, for this question, if you really pick up the green bin from the back, then we need to think the mixed pack where the x equal to x3 has the highest chance to be selected. So in other words, most likely we are picking up this thing, which is the mixed pack of the tic-tac. Okay, of course, I didn't say it's impossible to get the Liam flavor bin from the green box. That's also possible, but the probability is lower than the mixed pack, okay, which is 2 over 5, which is lower than 3 over 5. So I think the highest chance is given to the mixed pack. Okay, yeah, this is just the idea of this question here. And let's assume, so this question again, so let's assume you are the player of this game, Okay, in this part, we want to use the mathematical way to describe this example. So we assume we have already known the marginal PDF or PMF of the x and y, respectively. We know the conditional PMF as well. And if you are able to observe the outcome of this game, so y1 equal to 1, and we want you to evaluate the possible value of x. Okay, so this is the mathematical way for this question. And our answer is x equal to x3, which is 3, because that one gave us the highest value of the probability, which is 3 over 5, as we mentioned. Okay, so the player is most likely to be awarded since when the y equal to y1 equal to 1. So this PMF gave us the highest probability value. Okay, this is just the whole question. We have done the analysis, very simple case. But what we have analyzed in this question can give us a very important conclusion. If you have already known some of the observations, so for example, y to y, so I want you to estimate the income parameter, the x. So estimate a value of x is actually the estimation which can maximize this conditional PMF subject to y. Okay, mathematically, our biased estimation, I'm using the x height to denote it, is the value of the x. Argument means AIG for argument, right? The argument x, which can maximize such conditional PMF distribution. Okay, so I'm using the example to help you to understand this formula again, right? So in that example we mentioned, you pick up a limb variable bin, right? So that is known observation y. So y is the observation, is condition. So I put the y after the vertical bar as condition. Now, based on this observation, I want you to estimate which box of the tic-tac you open. So we are using this x height to denote it. Why can't we use just x? Okay, x, the lower x, is the real value you picked, is the real box you opened. But so far, we don't know which box you opened, so I don't know the value of the x. This x height is indicating my estimation, my best thinking, my best guess. Okay, so the one you really opened and your best estimation are different things. So we are using different notations. X is the real one you opened. The x height is our estimation, the best estimation. Okay. Okay. So how to evaluate which tic-tac is the most likely opened by me? Okay. So because y is known here, so I want to examine the distribution, so joint conditional PMF of the x. I need to pick up the argument x. So here again, you can see I want to find out the argument x, which can maximize this conditional PMF. Okay, this whole story. Now this is important for us. Okay, general description. In engineering, the idea of the estimation is the technique of being able to estimate a desired signal or parameter or variable value, okay, of interest given observation y. Now here we need to understand what does estimation mean. Estimation means you can observe y. So what is best, the highest chance, the most likely to happen regarding the x? Okay, this is estimation. And the notations used in the estimation process include the desired signal. In this lecture slides, we are using capital X, but in your future study in this unit, you may say sometimes we are using the signal N or signal Y to denote the desired signal. So the notation is not really important, but term will be important. So desired signal means the true value of the vulnerable X. The noisy observation is Y. So in this case, it's the bin you picked. That is your observation. In most of cases, the output, the Y, is noisy interference by something else. Okay, so this is the noisy observation. Our estimation is the best guessing of the X based on the known condition of the Y. That. And some other terms, so important terms, including the Pry distribution. The Pry is used to describe the input variable X. So the distribution of this X, the input variable, is called Pry distribution. So normally we use fxx to denote it. Okay. So in our example discussed here, so this fx, the Pry distribution, is talking about the marginal PMF of the tic-tac packs. Okay. And the next one, evidence. So this is easy to understand because we are able to observe some values, the conditions. So your observation is following the distribution, and we call such kind of thing as the evidence. So the distribution of the evidence is denoted by the FYY. Of course, again, this could be other letters, so like the N or x or depends on the questions. So y is just the letter we used for the example, but it could be anything else. Okay, that's a distribution of the observation. Next to may be new to you, posterior distribution. That is actually the conditional PMF or conditional PDF, depends on if the random variable is discrete or continuous. So the posterior distribution, the posterior means always you know the observation or condition of this distribution. You want to know what is the distribution of the x. Okay. Finally, likelihood function. That is the other around. That is another conditional PMF or conditional PDF. But in this case, the likelihood distribution or function means we know the distribution or the value of the input x. We want to predict what is the distribution of the y outcome. Okay, these are just all the notations and the terms used in our estimator analysis. Okay, now we come back to the same graph again. So I want to just again put all the factors together in the same graph so you know all the pieces and the relationships between each other. Okay, so all the marginal PMF and the conditional PMF remain same as the one we saw from the previous slide. But you can see next to each of these four terms, I'm using the red color to indicate the name or the nature of them. So regarding the fxx, that is regarding input variable, that is a prime distribution. For the output variable y, that is the something that we can observe that can be treated to be condition or evidence distribution. Regarding the two conditional distributions, so the first one, regarding this one, because the condition is subject to the y observation. So this conditional PDF or PMF is actually the posterior distribution. Finally, if the x is used as condition, so x is input, right? So if x is used as condition, so the conditional PMF or the PDF is the likelihood distribution. After we know all these terms, so regarding that relationship we analyzed before, they can be expressed by using this relationship. In other words, the posterior distribution is equal to the likelihood distribution multiplied the prime distribution divided by the evidence distribution. Okay. I don't really expect you to completely memorize this thing, but you need to understand how to use it. And I think this formula is really simple. You must be able to recognize which one is which and know how to use it. Okay. Okay, this is about what we are doing. So some background information regarding the estimators, which we are going to introduce here. And from this moment on, we are going to start the real content of this lecture. At the beginning, we mentioned in the first section of the lecture, I'm going to introduce two simple estimators. One is called MAP estimator, and the other one is called ML estimator. This MAP stands for maximum posterior estimate. Okay, now we have already studied what is posterior distribution. So the MAP estimator should be very easy for us to understand. We want to design an estimator which can maximize posterior distribution. This whole thing. Okay, so that's why we call that as MAP, because we want to maximize this posterior. But we said posterior distribution is actually the distribution of the x subject to the observation of the outcome random variable y here. In this case, this fx subject on y is the posterior, but we want to maximize it. So you can see here, we want to determine value of the random variable capital X to maximize this posterior. And the result, in other words, the value of the X, which can really maximize this posterior distribution, is our estimation result. So again, we are using the X hat to denote it. And the methodology used in this estimation is the maximum posterior estimation. So we put the MAP as a subscript. This means we derive this answer from the MAP methodology. But how to do that? Okay, let's just keep going. In the next line here, you can see we are replacing this posterior distribution by using its equivalency, which is given here. Okay, this formula was given at here, and also you can see the same thing from our, I think, week 2 lecture. Okay, so this thing is totally not new. Okay, we have learned that before. Okay, now we are reaching the second step, which is just a very simple replacement. But regarding the step 2 and step 3, you need to understand the reason. Okay, in the step 2, we got a fraction and in the maximization operation. At the bottom of the fraction is FYY. That is the distribution of the evidence. But do we need it in this maximization operation? The answer is no, because in this maximization operation, we want to find out the X value which can maximize the whole thing. If our focus are just different values of X, the Y value will not affect our decision. So in other words, in such maximization process, we can ignore the Y itself. So actually, between the step 2 and step 3, I'm deleting this Y distribution or the evidence distribution because it's nothing relevant to the X. Okay, but on the top, regarding that FYY subject to X, you can't delete it because X is involved in this calculation. Okay, by the end, we are reaching this result. This formula is the one we used to determine the MAP estimation result, X hat. Okay, this is continuous case. So for the discrete case, same story, but you just need to consider not the distribution function. We just consider the PMI function, or in other words, the probabilities. Okay, the result remains same, roughly the same thing. Okay, so meanings are the same. Okay, next we need to notice one thing. No matter continuous case or discrete case, so after reaching the very last step, so we know our estimation depends on this thing or this thing. So no matter which cases we are viewing, so we must notice this and this. If you want to know which X hat you want to get, you must know the prime distribution. Prime distribution is a distribution of the input variable X. Okay, we must know this one. But in many cases, the prime distribution is unknown to us. For example, if I want to use the MAP methodology to estimate the X value, so I want to derive the X hat by using such formula, and this is equal to this step. But if the prime distribution fxx is unknown, so you can't go any further. You stop here and without any answers because we don't know that. So in such case, if the prime distribution is unknown, so we have to use the maximum likelihood estimation methodology to estimate the value of the X. What's the difference between the maximum likelihood and the maximum posteriors? Okay, let's have a look here. So when the prime distribution fxx is unknown, we want to make an assumption to simplify the whole question. If we got a continuous random variables in the whole question. So we assume the distribution of the x, so in other words, the prime distribution, okay, is uniform. So can you recall what is uniform distribution? Uniform distribution means within, for continuous case, between a given range A and B of the x value, the PDF of this random variable x is constant within this small range, and its value is 1 over b minus a. Okay, and out of the AB region, so the PDF value of the x are all zeros. So this is the PDF of the uniform distribution. We also mentioned the uniform distribution means within the AB region, all the x values have equal probabilities or equal PDF to be selected. So this is the meaning of the uniform distribution. Why we can make such fair assumption? That is indicating if you got no information about x, so you have to assume all the possible values of x have equal probabilities. Just that. For example, for tomorrow, what is the weather of tomorrow? I don't know at all. So maybe 50% chance to be sunny, 50% chance to be rainy, just 50-50, equal probabilities, because I don't know that. I got no information on it. So I assume all the possible values have equal probabilities. Just that. Okay, for the discrete case, exact same thing. This is actually the example I gave. Okay, exact same thing. So all the possible values of the x have equal probabilities, which is equal to c. Like that. After introducing this assumption, now we can convert the MAP estimation to the ML, so maximum likelihood estimation. But how did we do that? Okay, in the second half of the slide, you can see on the left-hand side, we got continuous case and discrete MAP estimations. As I mentioned in the previous slide, so all the estimation by using the MAP can give us such formulas. And also we have such prime distribution. In this case, they are unknown. But because of the assumptions we made, so this fxx, the prime distribution, is following the uniform distribution regarding the x. And this fxx within the AB region is a constant. But a constant z is not affecting the maximization process. So c can be removed. C is nothing about the x selection. So c is removed. After we delete c, so we derive this answer. But what is this fyy subject to x? This is the likelihood distribution. So what we are going to do now is to maximize, or in other words, is to find out the x value which can maximize this likelihood distribution. And so this process is called the maximum likelihood methodology. Because you don't have the prime distribution, you do not have the evidence distribution. So only the likelihood distribution left. And you want to pick up the x value which can maximize this likelihood. And then we call this as maximum likelihood methodology. Okay, now we have done the discussion of the two simple estimators, MAP, maximum of posterior, and ML, which is the maximum likelihood, these two estimators. And the difference between these two estimators are, for the MAP estimator, you have to use, we go back here, you have to use such likelihood distribution plus your information or knowledge regarding your prior distribution to work out your result. But regarding the maximum likelihood this estimation because we assume the price are following the uniform distribution, or they have all equal probabilities. Then we can limit the knowledge requirement regarding the price information, price distribution. So the only thing left in this estimation is the likelihood. Okay, so first of all, we want you to understand the difference between these two estimators. And regarding the maximum likelihood, this estimator, you must understand what condition was introduced. And finally, for these two estimators, you must know how to do the calculation in a given question. Okay, this is just our first part of the lecture. Okay, after we understand the MAP and the ML, these two estimators, we are going to move on to our next section. In the next section, we are going to introduce a new estimator, which is called MMSE. This MMSE stands for Minimum Mean Square Error Estimator, MMSE. Okay, but why do we need to extend our MAP and ML estimators to this new one? Okay, let's have a look at this advantage of the MAP and the ML, these two estimators. So in this slide, you can see we are showing you the same example we used in the first section. Or in other words, the tic-tac game. The X is input variable. The Y is the output variable. So for the Y, we have two values. For the X, we have three possible values. So all the conditions remains the same as before. This question is very simple. If you really pick up Y equal to Y1, Y equal to Y1, and then the corresponding possible X values have only three possible options. So X1, X2, or X3. Even easier, so we have only two values, possible values for X, X1 and X3 only. So once you use these X1 and X3 values in that conditional PMF, so you can easily evaluate which X value can give you the maximum conditional PMF or PDF stuff. So very, very simple thing, because only two values to be compared. But if the systems becomes more complicated, in other words, for a given Y value, there are many, many possible samples of X. So the comparison will be hard work. In this new slide, you can see on the left-hand side, we got the easy case. So that is a tic-tac game one. But on the right-hand side, you can see in the graph, we have many, many sample points. For example, so we are using the right-hand side bottom one as example. At a particular Y3 value, okay, this Y3 is our condition or observation. In other words, the value of the output variable. Okay, so we have already known this result. Based on this observation, I want to get the best X value, which can maximize the conditional PMF and PDF. Okay, in other words, our best estimation of the X, either MAP or the ML, should be equal to the argument X, which can maximize, okay, can maximize the conditional PDF or PMF, this thing here. Of course, if you are using a MAP, maximum or posterior, so you have to have the distribution of the X. But for the ML, this one is optional. Okay, so this is just what we have done in the MAP and the ML estimators. Regarding a given Y3 here, okay, this Y is known. Now we are going to give all the possible values of X into this equation so that the maximum one is selected. In other words, the best X is able to give us the maximum this. Okay, so in this example, so far you can see if the Y equal to Y3, there are only two possible X values. Of course, this is not what I want to say. There may have many points. And if you want to pick up the best X, which can give you the maximum conditional PMF, you have to examine the corresponding values of x one by one and put that into this calculation, and then store all results together. After you got all such results, so compare them and pick up the maximum one. That one gave you the best x. So this process. But this process will be time consuming if the number of the x values are huge. And this may take a lot of calculation power as well. So in other words, this methodology is good, is effective, but may not be efficient if the sample space are large. So because of this reason, we want to find another efficient and effective way to evaluate the x height. So in other words, the best estimation quickly and efficiently. So it's why we need to introduce this minimum mean square error estimator. Okay, now first of all, you can see the name of it. But what we are going to do and how to do it is a problem. Okay, so we want to form an estimate for x. Okay, here. The final target is to solve the problem. What is the best estimate for the x? So this question remains same as before. So we want to use the observation to know the input value of the random variable x. Okay, but this is the target of this approach. But our methodology will be different. So regarding this estimation of the x, we want to form a function of the observation y. Now, in the next line here, you can see the x, this x is not a lower x. This is capital X, okay? So be careful with notation. This capital X means we are not going to determine a single value. So what we want will be a function. Of course, this function should be, the value of this function should be just the estimation of the x, okay? So x height means this is the function, the estimation function. Its function name is g, so this g is a very general function name. We talk about it later, okay? The parameter used in this estimation will be the random variable y here. In other words, we are going to use the random variable y as the parameter of g function to produce the estimation function of this system of the x. But what will be the final design or judgment carrier for this function? Okay, if this function is good, so we want to minimize the mean square error. What is the mean square error? Actually, we should understand two things. First of all, we have the true value of the x, and we have another thing, which is our estimation from the observation. So the true value of the x could be just x, and our estimation is the x height. In more than 99%, our estimation will not be as accurate as zero error. So that means between the true value of x and our estimation, there must be some difference. This difference is called estimation error, which is x, the true value, minus our estimation. This is why we call this as an error. And the next operation regarding this one is the square. So I will tell you why we need to square it, but the square error is it's just x minus x height. So we just square this error. The very last operation is the mean. Mean operation is actually the expectation of something. For example, the mean of x is the expectation of the x. The same thing, we want to calculate mean. That means we need to calculate the expectation of the x minus x height square. So this is the reason of this name. So the mean square error involves 3 different steps. First step, find the difference between the estimation and the true value of the x. So this is error. Next one, square this error. Very last one, calculate the expectation or the mean of the squared error. Okay, mean square error is coming from here. Okay, so after we understood what is a mean square error, so here we introduce a notation. We are using a letter E, so normally lower E, to denote such mean square error. This new estimator we are introducing in section is called minimum mean square error. So in other words, if we can run this estimator very well, so the mean square error of our estimation will be minimized. So this M is for minimum, then mean square error. We want to minimize the MSE of our estimation. Okay, so this is what we are doing. And the X hat is known as the minimum mean square error estimator. So in other words, this X hat is called MMSE estimator. And its function is G, as we defined. Okay, the X hat is actually G function. And I think the next step will be not hard, but important. Okay, please be careful now. In this formula here, the first letter is not capital X anymore, it's a lower x. This lower x hat is indicating this x hat is one particular value of that capital X hat function. Okay, so in other words, once you got this function gy ready, so this estimator is ready, and then we can observe one value from the outcome random variable of the system. So y is known. So we put this y into this function, and the corresponding function value is the estimation value based on this given observation. Okay, that is just what happened regarding this one. And we keep going with the formula. So in the middle step here, so between here and here, I think you can find this G is a little bit weird. There's a star there. So what does star mean? This star means the best, or optimized, or optimal. That means this G function has already been the one which can give us the minimized mean square error one. So this is our selection, which can give the best result. So we call that as an optimal estimator, the best one. Okay, but how to determine the best G function as our estimator? Okay, this G star, the optimal estimator, comes from here. Because we mentioned, if this mean square error estimator is the best one, it must be able to minimize the mean square error. But how to just use a mathematical way to describe its capability of minimize the mean square error? This one is given here. You can see argument. So we want to determine the argument of this function. The argument is the G function. This argument of G function is able to again minimize what? Minimize our mean square error. Okay, this is the whole story. In other words, within this function, our target is not to change x, it's not to change y. Our target is determine the G function. And we want to determine which best G function can give us the maximum the function here. Sorry, minimum. Which G function can give us the minimized value of this mean square error function. Okay. In the meantime, so okay, the formula from the beginning up to here has been explained. That's okay. And what is the very last thing? Very last segment here. This part is indicating you have already known the y value as condition, and our estimation of the x value should be the expectation of the random x value. They should be compatible between each other. So we put this in as the very last piece of this equation. Okay. And now we just introduced the concept and definition and the mathematical formulas. You may not be able to fully understand what happened. So let's just use the example again to tell you what happened. So at bottom of the slide, you can see two graphs. So on the left-hand side one, that is the one with a lot of scatters in the y and x plane. But in this case, because we are going to use the observation y as the parameter, so I put y as the horizontal axis, and x will be the vertical one. Okay. Now, from these small dots, you can see we have already got a lot of samples. And now what we are going to do is to do the estimation. But we don't want to use the MAP or the ML anymore. So what we are going to do based on the introduction of this slide is we are going to construct a function. This function is x height equal to gy. So in the graph on the right hand side, you can see I'm plotting a red color line. This red color line is our linear function, which is x height equal to y minus 3. You may temporarily treat this line to be the so-called best fitted line to all the scatter points. Okay, so in such case, we assume this one is the best one temporarily. Okay, so at a particular moment, you pick up, okay, my random variable y, the outcome variable, is equal to y3. Okay, this is the point I pick. At my observation, I have known this value. Based on this value, y3, I want to know what is the corresponding best x. Okay, if you are doing the MAP or the ML estimator, so you have to, okay, we go up, pick up the corresponding scatter points and find out the x values, and then compare them, and which one can give you the best, the maximized conditional PDF or PMF. Then that x is best one. I said, no, that is time consuming and require a lot of calculation power. We don't do that way. What we are doing is we just start from the y3 point and go up to our minimum mean square error estimator function curve. In other words, the red line in this graph. And then we go to the vertical direction and find the value here. This value is our x3 estimation. Okay, what is the value of this x3 estimation? This x3 estimation is equal to y3 minus 3. This comes from our function, but we put y equal to y3 into this estimation. By doing this way, we don't make any comparisons. We just use one single function, put our observation as parameter inside, and then produce the function value. That value is our estimation from this minimum mean square error estimator. Okay, so that's very simple thing. This can save a lot of time and power, calculation power. Okay. So after this one, I believe you have already known so how we run this thing, but then you will have more questions. In the following slides, we are going to give you more details on this MMSE estimator. But here, we want you to just understand more things regarding the MMSE estimator. So where is the estimation error? Is that, okay, you pick up y3 as your observation, so this is known, and then the corresponding x3 height is determined or derived by finding the corresponding value from this MMSE estimator. Okay, that's easy. So we have already known this thing, right? But in the meantime, at y3, it must have the corresponding true value of the x. This x3 height is our estimation based on this estimator. But what is true input value of the random variable x? Okay, it may be x3 here. Okay, we have said the true value of the input to the system is x3, but our estimation based on this estimator is x3 height. What's the difference between them? It's different. Or the estimation error is x3 minus x3 height. In the graph, this x3 minus x3 height is just this small blue color segment vertically between the x3 and x3 height. Okay, everyone sorry for point given in this graph. I think this E3 is very confused because we introduced the E stand for the mean square error. So everyone please ignore this E3, okay? So I don't want to just confuse you, okay? And this blue segment, it just indicates the difference between the true value of the input general X with our estimation. So that easy stuff. Okay, more questions are given here. You may just ask me, if I want to judge if minimum mean square error estimated is good or not. So what criteria will be used? Can I say if the x3 minus x3 height small, then my estimate is good? Generally, the answer is no. It's not enough because when we construct this estimator function, it covers all the possible scatters or the sample points from the x and the y. So if you focus on a small error between only one single estimation, so 1 point, that's not good enough because we need to consider so how to give the best average performance over all the samples, not a particular one sample. Okay, this is the first point. So one single error, small error, is not good enough. But how about if I can give a small average error, will it be good? So in other words, if the mean value or expectation, of course, of the x minus x height small, is that good enough? Answer is not enough. Because for a fixed value of the x, our estimation may sometimes higher than this value or sometimes lower than that. So such kind of higher or lower can be corresponding to a positive error or negative error. If you just want to calculate the mean value or the expectation of such errors, x minus x hat or x plus x hat, whatever, something like that, so these errors may cancel with each other. And the final result of such expectation cannot really reflect the average behavior of the x height. Okay, example here. We assume this is the true x value. This is true value. And our estimations may add here. In the first time, our first estimation is here. And in such case, because the x1 height value is higher than the true value of x, so its error here is negative. Why negative? Because we are using x minus x1 height, but the x1 height is bigger. So that means this error is a negative one. But sometimes our estimation is lower than the true value of x. This is called x2 height. This is lower, right? Then the error is x minus x2 height, which is greater than 0. You can repeat this one for different estimations and got positive, negative, positive, negative. By the end, you will got a number of integers or whatever higher than 0 or smaller than 0 as the errors. When you calculate the estimation of x minus x height, okay, all these positive values and negative values will be combined together to work out the expectations. But these positive negative values will be cancelled between each other. By the end, in some cases, you may say that expectation is 0. Some extreme case, okay, is 0. This means, okay, in my estimation, the result is so accurate. It's very close, very, very close to the true value because its estimation is 0. I mean, the estimation of the error is 0. No error. It's so good, right? But the result may not be true because in your estimation, you may have huge errors. The reason you see the final value of the equation is 0 is just because the positive huge error is cancelled with the negative huge 0. You can have the huge difference, but you can't observe them from this equation. Okay, so because of this, in the second point here, the small average error is not good enough. But what will be the criteria for the judgment if MMSE estimate is good or not? Okay, we must minimize the mean square error. Now you can see the importance of this square. So what does square mean? Okay, we keep using the example. Okay, now you know we have a number of estimations and compared with the true value of the x. So some errors have negative errors, but some samples, some estimations may have positive errors, right? But if you square all this difference, all the negative difference will becomes positive, because negative something square must be positive. And then when you evaluate the expectation or the average of the squared errors, that give you a number. This number must be able to indicate what is the average performance of your estimation, because the positive and negative thing will not be able to cancel each other. All the errors were converted to positive before we evaluated them in the expectation. Okay, so this is the reason we use the square here. So everyone, please bear that in mind. So in the MMSE estimators, we focus on the average performance of the mean square error. Okay, we should try our best to minimize the mean square error. Okay, this is the reason we select the mean square error minimization as the judgment criteria. Okay. Before moving on to next slide, so let's just quickly summarize another important point. So how to say an estimate is good or not? Of course, the one which can minimize the mean square error is the most important thing. Another 2 points you need to notice is, first of all, a good estimator should be able to minimize the mean square error. Smaller mean square error is always better. When the estimate is perfect, so estimation should be exact same as the true value of the x, and by then the mean square error will be 0. But this is too ideal. So in most of cases, this is impossible mission. But we should try our best to minimize the mean square error, of course. Okay. Another important criteria is the estimator must be unbiased. What does unbiased mean? This means the expectation of your estimator should be the same or matching to the expectation of your original input x vulnerable. If your estimator is biased, this means the expectation of the estimator or the average performance of the estimator will not be equal to the average of the vulnerable. This is called the biased estimator. This is not good because your estimation cannot match to the performance of the original vulnerable. These two things are not expected to be the same. Of course, the estimation is not good. It's a very poor one. Okay. Okay, this is just all the important criteria used to judge if MMSE estimate is good or bad. But not the end. We'll move on to the next part. We have 2 examples. Okay, this is the example 1. This is the example 2. So in these 2 cases, we have a number of the scatter points. We mentioned maybe by using the minimum mean square error estimator, we are able to construct our estimator to be a function in terms of the y vulnerable. And based on the positions of the sample point, actually we are constructing 2 different functions for these 2 cases. In the first case, so on the top row, based on the position of the dots, the best, so-called best fit line, the function curve of our MMSE estimator looks like a straight line going up. But in the second example, you can see it's very hard to use a single line to represent the MMSE estimator in the second example. And we'd like to use another curve to match the position of the dots. And based on the shape of the curve for the MMSE estimator, we can treat them to be first order MMSE, the linear one, like a single line, or using the curves to represent them. In the second example, the order number is higher than 1 because it doesn't look like a line. It looks like a second order function curve. So in this unit, we focus on the first order MMSE only. So in other words, we do not need to consider second order or higher order estimators. So yes, in the real world, in the industry, they are using the second or higher order MMSE, but it will take a long time to design such estimators. That is too complicated and out of scope of this unit. So in our discussion, we focus on the linear case only. But for the linear case, okay, we want to construct x hat equals g y. This g function must be the first order or linear case. But how many linear cases you can see or you can think? Okay, we have 3 options here. First case, x is equal to a constant. You don't need to worry about the b or the star or something like that. But you just look at this graph. You can see this is a line. So this is a linear thing. Even though we don't have the b in this g function, we don't have the y variable in this g function, but this is still a line. So this is a linear case. And this line may be mean square error estimator. I think yes. Okay. And the second option is this one. In this case, the g function is equal to a by y. A is a constant. A by y means this is a linear segment crossing the origin, going up or going down, depends on the value or the sign of the a. Right? And the case 3, x equal to ay plus b. This is still linear case because the order number of the y is 1, right? So this is still linear case. And from the graph, you can see it's going up linearly. Of course, it can going down if the a is negative. But compared between the second and third cases, you can find we are adding a b value here. That means the compared with the second graph, this linear segment will be shifted up or down by b deviations. Only these 3 cases, nothing else. If we talk about linear minimum mean square error estimator, there are only 3 cases to be considered. So flat, so x equal to b. Second one, go up or go down, crossing the origin. So x equal to ay. The third one, x equal to ay plus b. And this is linear as well, but not crossing the origin. That's these 3 cases. Okay, now we are going to examine them one by one to see are they biased or unbiased estimator. Okay, case 1. So x is equal to a constant b here. And you can see we call this as a constant curve. Of course, it's constant because the y is not involved. And let's just use the formula we studied to analyze this one. First of all, what is a mean square error? Mean square error equal to the expectation. So expectation is given here. Square is given here. And then this one, x minus b, should be the error. Of course, that's true because x is just a random variable value itself. The b is our estimation because x hat is equal to the b. So we are using the true value of x minus our estimation to get the estimation error, and then square it, and then do the expectation to get the mean square error. So E is our mean square error. But you may notice one point here. No matter what is the value of this x random variable, our estimation is always b. The b is constant. But in this case here, we mentioned, if you want to be a good estimator, you must be able to minimize the mean square error. So now let's try to minimize it. So we are using the E star as the minimized error, the minimized mean square error. Okay, But if we are using such x height equal to b estimator, so what will be the value of this minimized mean square error is calculated by using this way. So first of all, we want to select the best b value, which can minimize such mean square error. Okay, it's a little bit messy, but I hope you can read it. Okay, we want to determine the b value so that the mean square error can be minimized. And regarding the expectation, we can write that corner here. Okay, this is equal to x squared minus 2bx plus the b squared, which equal to x squared minus 2ex by b plus the b squared. This result is given here. You are going to minimize this thing to derive the best result. But if you want to minimize a function, so in terms of b, so we want the derivative of this function with respect to b is equal to 0, so that the function value is minimized. By setting the derivative of function with respect to b to be 0, we can work out the best b value is equal to ex, the expectation of the x vulnerable. Of course, yes, this is true, because your estimation x height function is just a constant. So the best b is, of course, the expectation of x. This is true, but this is not a good result. See here, after using the b star as our parameter, so in other words, after this step, we know the best b value is the expectation of x. So we got the x height equal to ex. Did you see something here? Let's recall our story. We want to have to improve the estimation of the x based on the observation of the y value. But in this result here, our best estimation comes from the x without the y. But the y can be observed. Y is conditioned. Y is what we have known. But we are not using this known condition to estimate the x. That means this x estimation is totally independent of y. Okay, so this whole thing here. This is not good. That is indicating we are producing our estimation without using the known condition. If you do not use the known condition, so when you estimate the x, you do not have any clue on it, right? Okay, now let's have a look here. The b star is equal to the mean of the vulnerable x, and the minimized mean square is the variance of the vulnerable x. So actually, very simple calculation into the beta. Okay. In the x equal to b star in this estimation, in this estimator, the evidence y is not used. The estimation of the x relates to the prior of the x only. In other words, this estimator is useless at all because you are using the x vulnerable information to get the x estimate resulting in y. This is not an estimator. Okay. Okay, this is the first one. Please bear that in mind. If the estimator linear minimum mean square estimator x height equal to b is used, result will not be good. Okay, because you are not using any observation to help you to improve your estimation. How about next one? We mentioned that there are 3 cases, right? So this one, yes, it is an estimator, but definitely not good. Okay. Now we are going to move on to the next one. So if the x height equal to a by y, okay, we are using our observation y here. So what will be the result? Let's have a look here. This is the x hat equal to gy equals a star by y. A star means the best A, of course. Okay. This is a linear curve, but biased. First of all, repeating what we have done before, so we are going to evaluate the minimized mean square error. And in this case, the A will be determined. Because if you want to minimize such mean square error, so the derivative of this thing must be equal to 0. Okay, of course, it needs a couple of mathematical inductions, but finally, we can find the result of A star, the best A, which can give us a minimum mean square error. The best A is the equation of the x by y divided by the expression of the y square. Okay, this is A star. Once we know the A star, so we can just put that back into our estimator. So x hat is equal to A star by y, which is equal to the expression of x, y product divided by the expression of the y square by y here. And then, don't forget, there's one rule for us to judge if an estimate is good or bad. Such rule is we want the expression of the x star to be the same as the expression of the x vulnerable. So in other words, we want to examine, are they the same, to judge if this x equals to ay is good or bad. Okay, so we want to calculate the expression of the x hat, which is equal to the expression of exy divided by y squared then by y. Inside of the expression, this term should be a constant because we said the expression of vulnerable is actually constant, right? So this one gives us exy divided by y squared. We move this one out of the expression. Then inside of the expression, there is only one single y left. You see. Is that equal to the expression of x? Normally, no. So you can see here, normally they are not equal. If they are not equal, so this estimator will not be good because its estimation cannot match the behavior or average behavior of the original vulnerable. This is called a biased estimator. Okay, so that the bias means not very good. Okay, but if you use such estimator, so let's just keep going one more step. Okay, when the optimal A is selected, so in other words, when this A is used in such estimator, the corresponding minimized mean square error is equal to this one. Okay, but even though you reach this result, this estimator is still not good because its expression is not equal to the expression of the original vulnerable. Okay, so summarizing, if the x equal to ay, it must be a biased estimator, and this estimator is not very useful in the real world. Okay, now out of all three linear minimum mean square estimators, we have already examined two. There's only one left. So x equal to ay plus b. Okay, that's the very last one. Let's have a look here. Here, x hat equal to gy equal to ay plus b. Same as before, we can just evaluate what is the minimum mean square error. But we want this minimum mean square error to be 0, to be minimized. So the derivative of it should be 0. Again, we want to minimize this mean square error. So the derivative of this mean square error is supposed to be 0. By using this idea, we can evaluate the b value. And do the same procedure, we are able to determine the A value. So this B value and the A value, which can minimize the mean square error, are called the optimized B and A values. After you finish these two steps, the B star, A star, the best values of A and B have already been determined. Put that back into your linear minimum mean square error estimator. So we got X hat equal to A star Y plus B star. Okay, that's the easy step. And then the next step is pretty simple. We just put the A values, B value into this function to get this one. This is our linear minimum mean square error estimator. Okay, for such filter, for such estimator, is expectation is the same as the expectation of the original generable X. So this is an unbiased estimator. So this is a good thing. And if we are using the A star and B star, the best values of them in this estimator, so the corresponding minimized mean square error is calculated here. So very simple thing. You can do that yourself. Okay. This result and also this result are important. Okay, because out of all three linear minimum mean square error estimators, only this one is useful. Only this one is an unbiased estimator. The other two are totally useless. And because this one is the only useful estimator, you must know, first of all, how to determine the A and B, the value of these two parameters, the best values of them, And also, you must be able to know how to evaluate the minimized mean square error. So these two formulas are doing that. This is indicating when we got the best function to estimate the X hat. So what will be the error estimation? Okay, like that. For the bottom summary regarding this X equal to AY plus B estimator, first of all, this function, this estimator is an unbiased estimator. And second point, even the A star, B star, the best values, optimal values are employed. The minimized mean square error is still non-zero. That means our estimation will not be 100% correct. We still have small difference. Okay. Finally, the estimator performance relies on how correlated the Y is with X. Here, the reason of that is we have, so I remove this part, you can see that we have covariance X and Y here. We have the correlation coefficient rho XY here. These two things are used to evaluate the linear relationship between X and Y. So the total value of the minimum mean square error E star depends on rho XY and the covariance value of the XY. So if the X and Y are totally no relationship, no linear relationship, the covariance of the X and Y and also the correlation coefficient rho XY will be equal to 0. If this term is 0, you can find the E star is just equal to the variance of X, not the business of Y. Okay, this means Y is useless. Of course, this makes sense because if we said the rho XY equals 0, the Y and X doesn't have any linear relationship. Of course, knowing the Y will not be able to help you to understand the X, cannot be helping you to improve the estimation of X. Okay, so in other words, the linear relationship between X and Y are very important for your linear minimum mean square error estimator. Okay, that's that. Okay, the very last topic for this part, the orthogonality principle. So actually, this is a small extension from our linear minimum mean square error estimation. So when we consider the minimum mean square error linear estimator here, we want to evaluate how to minimize the mean square error. This is our mean square error, right? And with that, the only useful estimator for this case is x hat equal to a y plus b. Now this x hat is substituted here, and then we can derive x minus this, because we are using a y plus b to replace the x hat. Okay, and then what we are going to do is to minimize this mean square error. So by minimizing it, we want the derivative of this mean square error to be 0. So we want the dE over dA to be 0. Of course, we have the B issue, but for this topic, we focus on A temporarily. Okay, so this gives us, we want to find the derivative of expectation of x minus ay minus b square with respect to the a to be 0. In this derivative calculation, only the a is our focus. The x, the y, and b are not related to our derivative calculation. So this is giving us that such derivative equal to 0 can be converted to expectation of, because it's a square relationship, so we move 2 here, 2x minus a y minus b, 2 minus 1. And then multiple, because our focus is the a, but for this a, it has one coefficient, negative y. So you have negative y given here. We want that to be 0. And then let's just remove some constant. Number 2 is constant, nothing related to random thing. So the expectation of such thing is no relationship with number 2. So we can move number 2 out and divide by 2 on both sides. So this thing is gone. So we remove this 2 here. 2 minus 1 is 1. So we don't need to worry about that. And negative sign doesn't matter. So negative sign is negative 1. The expectation of negative something is same thing. We can move negative 1 out of the expectation. So negative is moved to the front. And then cancel it on both sides. So it's positive. After this step, we got expectation of x minus ay minus b by y equal to 0. The first term, we call that as term A. The second term is term B. Now we need to link this equation back to our question. What is y? Y is our observation. Okay, y is the condition. Okay, what's A? A term here is actually x minus ay minus b is x minus ay plus b. But this ay plus b is our estimator. So in other words, this is x minus x hat. This is our estimation error. So in other words, we can say the A is the estimation error here. The B is our observation. The equation of A by B equal to 0 is indicating that the relationship between A and B is orthogonal. Actually, what we have known from this calculation and this calculation is saying the estimation error and the observation are orthogonal between each other. The expectation of the product between these two things is 0. Okay, this is called orthogonality principle. Okay, So actually in this slide, we are talking about this thing. You can see the expectation of the estimation error and observation is equal to 0. Okay, this is called orthogonality principle. So officially, the orthogonality principle for mean square error estimation states the estimation error is orthogonal to the observation data. This is very important for our discussion in the chapter 2. Okay, and this thing may be reused in the chapter 4 again. Okay, and so for helping you to memorize this relationship, so I call that as EEOO. This is used to memorize the relationship. So estimation error is orthogonal to the observation. EEOO, very easy to memorize. Okay, so this is the most important rule of the orthogonality principle. So that very simple thing, right? Okay, the very last piece thing is about the general linear estimations. So in our previous discussions, we just say we have one single random variable y here, and we have one random variable x here. But actually, if we extend this to multiple division things, the rules remain the same. So now from this moment on, in the following slides, we are going to say extension to this linear minimum mean square error estimation. So we are going to consider multiple random variable cases. First of all, the desired signal from this slide and later slides, we are using the capital D to denote the desired one. This is actually the original one, is the X for the previous examples. Okay, so this is the true one, the true value of the variable. And the observations or the conditions are denoted by the X terms, so X1, X2, until Xn. So in this case, it's not a single observation. It should be a group of them. Okay, and our target is to estimate or to produce an estimation d hat. This d hat is a linear combination of the observations. The difference between the desired signal d and the estimation is the estimation error, d minus d hat. And the mean square error is equal to, that's easy for you. So square the error and then calculate the mean value or the expectation of it. So our target in this case is, of course, to design this estimator. But this estimator is fully described by the combination of all the A1, A2, A3 until AN, the group of the coefficient. So we need to choose this group of the coefficient to minimize the mean square error. Okay, so this is just the whole system. Okay. Now we want to just apply the orthogonality or the orthogonality principle. In other words, the estimation error is orthogonal to the observation. In other words, again, I just want to help you to recall what is orthogonal. Orthogonal is the expectation of the product equal to 0. The product between two things. One is the observation, right? But in our notation in this part, the observations should be a group of X random variables. Okay, and we want to put our X thing here. This is just the group of the observations. And the other thing will be the estimation errors. The estimation error is the difference between the desired signal with our estimations. Okay, this is the idea about how to use the orthogonality principle to finish the design of the estimator, linear minimum mean square error estimator. And in this part, this d hat, we have said the d hat, our estimation should be the linear combination of the observations. So the d hat is actually equal to, okay, you can just see here, is just the linear combination of the observations, right? So it's just the A1 x1 plus A2 x2 again until we reach the very last one. So we assume there are n observations available. Okay, so this is just the background of the thing. And then in this slide, we are trying to simplify this thing to reach our result. Okay. In this slide, the first formula is saying the observation error. Oh, sorry, my fault. The estimation error and our observation are orthogonal. And the next step, I just give this particular observation to all the elements and to extend to this step. And next step, I gave this iteration operator to each of these terms. And then we got a sequence of the estimations. The sum of them is 0. Of course, some of them have negative signs, okay? And then we define this thing to be the RDI. Okay, you must understand what does mean. Equation of D and XI. XI is the ice observation data, and this D is the desired signal. In other words, this RDI is actually the correlation between the desired signal and the observation data. Can you recall what is the correlation? If you have two random variables, just background thing, okay? X and Y. Remember we said covariance of the X, Y equal to the correlation of the X and Y minus mu X, mu Y. So for the single random variable case, right? And this is the correlation between the X and Y. This is actually equal to expectation of X, Y, and then the remaining thing is the same. In other words, the correlation between two random variables is actually the expectation of the product of the two random variables. Okay. For this case, you can see inside of this expectation, the D, the desired signal, is random variable, right? The XI is also a random observation data. So the expectation of the product of them is actually the correlation between them. Okay, this thing here. And for the remaining terms, like this one, and this one again, you can just take the constant A1 or A2 or AN out of the expectation. And then the remaining thing will be just EXI by by XJ. By X. J is here. What is it? This is the correlation of the Xi and Xj. Okay, so after we understand these notations, by the end, we can use these new terms to replace the original expectation operations. And then we derive this answer here. Of course, we move the first correlation to the right-hand side. And the result is showing the summation of the correlation, the linear combination of the correlation between the observation data is equal to the correlation between the desired signal and the particular observation data. This is for the Xi, this particular observation data only. If you repeat this for all the observation data, X1, X2 until Xn, you will generate a matrix. Okay, so in other words, this is for X1, for X2 observation data, again, until you reach the Xn observation data. That all true, the same thing, right? Then we can use a matrix format to organize these equations. Let's just assume the Rx equal to the expectation of X matrix by the transpose of the X matrix. In other words, this Rx is the correlation matrix of the observation data. So we learned this one in the week 2 lecture, okay? And this lower R dx is a vector. And it should be a common vector. And the elements in this vector are the correlation between the desired signal and the observation data. And finally, A is just a group or a vector of the coefficients regarding the estimator. So our target is to determine the A. Okay, another group of new notations, right? So we want to convert all these equations in a compact matrix form. So by using these notations introduced here, these groups of equations is summarized into such one single equation. So the correlation matrix of the observations matrix, of course, multiple the vector of the coefficient of this linear minimum mean square error estimator is equal to the correlation between the desired signal and observation. Okay, looks pretty long, but this is really compact form and very useful. Everyone, if you do not understand this, you must read this part. Very important. Don't forget, how did you derive this final equation? This comes from the orthogonality principle. Okay. But don't forget, the final target for our discuss is to determine our estimator coefficient, the A. But for this case, if you want to solve the A, you have to move the Rx from left-hand side to the right-hand side, so that on the left, we have only the A left. But how to move the Rx from left to right? Don't forget, Rx is the correlation matrix. So if you want to move the Rx from left to right, you can't divide it. You have to use Rx inverse. Left multiple the Rxa equal to Rx inverse multiple this correlation vector. And Rx inverse by Rx is an identity matrix by A equals Rx inverse by Rdx. Identity matrix by a vector is just equal to vector. If we got this result. But because we derive this thing from the orthogonality principle, but if something can satisfy the condition of the orthogonality principle, that mean square error must have already been minimized. Or in other words, if you derive this A from this orthogonality principle, this A must have already been the best coefficient of this estimator. So, in other words, this is actually the optimal A value. Of course, vector, of course. So you can see the optimal linear estimator vector is equal to this stuff. Okay, now after this long calculation, we have already known this best optimal A value for the estimator. After you design these A values, this coefficient for the estimator, we want to use it to produce our estimation. So the A value is used to multiply with the X observation. The result is our estimation. Why do you do this way? Because we said, let's record this here. The estimation D height is the linear combination of the observations. This doesn't given here. Because of that, so our estimation is the A vector transpose multiple the observation. Okay, now we have already designed our linear minimum mean square error estimator. We have produced the estimation by using this estimator. But after you produce your estimation, what is the estimation error? Or in other words, what is the minimized mean square error? That thing is given here. Same thing. We want to, first of all, evaluate what is the estimation error using the desired value, the true value of the D, minus our estimation. So this is our estimation. The difference between them is the estimation error. We square them and then calculate the average value. The result is the minimized mean square error. Okay, that is the general linear estimation topic. by the end, you can see at bottom, we gave this equation a particular name, which is called Wiener-Hopf equation. Is talking about this one. From this one, we are able to solve the coefficient, the optimal coefficients for our linear minimum mean square error estimator. Okay, so the Wiener-Hopf equation may be used in our chapter 4 discussion when we talk about IFIR filters. Okay, so this will be reused. Okay, everyone. So this is the main contents for the third part of chapter 1. And up to now, we have already finished all the contents of the chapter 1. And next week, we are going to start the chapter 2.